Hi, I'm Verstraeten. I'm a product manager in OCI and I'm dedicated to OKE and container instances. I delivered many features in OKE over the past few years, especially on the security topic. I'm passionate about making Kubernetes experience simple and secure. I wrote a popular blog post about OKE security titled Kubernetes Security, 9 Features to Secure Your Workloads.
Hi, my name is Alan Chester. I'm a product manager with the OKE product within OCI. I currently work specifically with security and governance with containers. This includes integrations with other Oracle security products such as CloudWorld. Previously, I worked on a team that built an internal Kubernetes platform to host Oracle SaaS applications, where my focus was ensuring security was built into this platform from day one.
And this session is about the best practices for secure application deployment in Kubernetes. We organized the presentation into 4 parts. The first is defense in depth, and then we'll talk about securing Kubernetes, then securing your containers, and finish with the threat monitoring. Oracle believes security should be at the foundation and built in the cloud, and customers should not be forced to make trade-offs between security and cost. Oracle is focused on helping to reduce risk by providing a comprehensive set of simple, prescriptive, and integrated security capabilities to help you secure your cloud workloads, data, and applications. OCI Container Engine for Kubernetes, or for short, OKE, provides you with secure and easy-to-use managed Kubernetes clusters in OCI. With OKE, you get the peace of mind to run mission-critical applications on Kubernetes, knowing that your clusters and applications are protected from malicious activity. The security of your Kubernetes clusters come with multiple layers of security hardening and features. Networking is the first layer. It provides you with the defense against unauthorized low-level connection to your clusters and application. Then access. OKE integrates with OCI identity and access management to provide users and application with the right authentication and authorization. For your clusters control plane and data plane, OCI and OKE follows industry standard to keep hardware and software as secure as possible. OKE provides regular upgrades of the Kubernetes software, patch the operating system, and enable you to patch your container images so you stay ahead of security vulnerabilities. All your data is encrypted by default in OCI, and OKE provides the option to control the lifecycle of the encryption keys. OKE provides the right mechanism to detect any suspicious behaviors and act to remediate any breaches. In this session, we are going to elaborate on some of the security features you can adopt to secure your clusters and application. We will first discuss the cluster security hardening. Second, talk about securing containers and your workloads. And finally, we'll address ongoing threat detections. Next slide. And so the first part is about securing your Kubernetes clusters.
One of the first lines of defenses for your containerized workloads is the networking in and out of your cluster. It is important to ensure a tight network perimeter around your Kubernetes cluster to defend against unauthorized actors. It is equally as important to also protect your egress out of your cluster to prevent data exfiltration attacks. When looking at securing the networking of your Kubernetes cluster, we typically look at 3 different components. First, the Kubernetes API, which is the entry point into the Kubernetes container orchestration and can be used to manipulate running workloads on your cluster. Second are the worker nodes. These nodes are actually running your active containers, and if this node were to become compromised, can be used to gain access to containers and other compute instances within your tenancy. Finally, we look at the load balancers that are used to front the services exposed within your cluster. Based on these components, Oracle recommends that you deploy your Oki cluster as a private cluster. This means both the Kubernetes API and the worker nodes are only exposed in private subnets within your VCN. They are not accessible on the public internet. In addition, customers should use network security groups to define the least privilege ingress and egress rules for all subnets, including your load balancer subnets. This helps to reduce a potential attack surface by only allowing authorized sources. Finally, since your cluster is private, the OCI Bastion service can be used to create a secure and ephemeral connection to your Kubernetes API for operational access. While it is important to properly configure your cluster's network perimeter, it is equally as important to also ensure inter-cluster networking has been properly secured. Typically within Kubernetes, you can leverage network policies to ensure ingress and egress controls are in place for service-to-service communication. As an added level of security, you can leverage OCI Service Mesh to apply both service-to-service authentication and MTLS between microservice to microservice communication. In addition, beyond the security benefits you get from using Service Mesh, customers will also gain the operational insights through the observability you gain between your microservice to microservice connections from OCI Service Mesh.
When network access to your cluster is enabled, users need authentication and authorization to access the Kubernetes API endpoint of your cluster. To achieve this, OKE natively integrates the cluster with OCI Identity and Access Management, or IAM for short. OCI IAM provides strong user authentication to access your clusters and provide you with the authorization to use the OKE API, allowing you to define cluster administrators and cluster users. Following the principle of least privilege, your users can only access the Kubernetes resources that they're authorized to. Kubernetes role-based access control, or RBAC, is aware of OCI users' identity and can bind user Kubernetes roles to OCI groups and users. Moreover, you can apply the Kubernetes role definition and the binding to OCI groups across multiple clusters. So let's take an example. You have a Kubernetes namespace X, and you have an OCI group Y that includes OCI users responsible for managing, deploying in the namespace X, and you bind the role to the OCI group Y. As a result, all the users in OCI Group Y can create and delete any application in the namespace X, but not in any other namespaces. Administrators can simply add or remove members to and from groups using the OCI console or the API. The authentication of a user who makes Kubernetes API requests through the kubectl CLI rely on an encryption key. While this authentication method is strong, you might want to add a second factor to complete the authentication. OKE supports IAM multi-factor authentication, or MFA for short. With MFA enabled in IAM, when users connect to the Kubernetes API, the encryption key is checked, which is the first factor. And then users are then prompted to provide the second verification code from a registered MFA device, such as a phone. That's the second factor. The two factors work together, offering an extra layer of security to verify the user's identity and complete the authentication process. Next slide. On the topic of security and access management, we are very excited to announce Kubernetes workload identity in OKE. This feature will be available after Oracle CloudWorld. Kubernetes workload identity provides a secure and straightforward method to authorize specific pods to make OCI API calls and access OCI resources. You can apply IAM policies to the Kubernetes service accounts associated with your pods. With this feature, you can apply the principle of the least privilege for your applications running in your Kubernetes cluster. Not only you can apply IAM policies to whole worker nodes in your cluster, but with it you can also apply IAM policies to specific pods. You don't need to store user credentials as secrets in your cluster. The OCI API request your application makes by using the OCI SDK or the CLI are authenticated by OCI IAM without additional credentials. And OCI audit logs tracks the API calls that Kubernetes pods make. And in OCI, those pods are now considered, with this feature, are considered as resource principal. So for example, you can authorize a containerized application to access objects in OCI object storage. Or you can authorize a container application to access secrets in vaults. The key in this feature is that only the authorized pod will be able to get access to those resources. And that access is managed centrally in OCI IAM. Next slide.
By default, all data created by OCI services in OCI is encrypted. However, if your containerized workload is storing either data in a persistent volume or maybe even sensitive material in the Kubernetes secrets, it's recommended to encrypt this data. Using OCI's Vault service, you have the ability to create your own encryption key. This key can then be used to encrypt boot volumes, your block volumes, and finally encrypt the etcd database that Kubernetes uses for its control plane. This is extra important since with this encryption within the Kubernetes secrets, these are backed and stored within that etcd store. And secrets are often used to inject sensitive data into your Kubernetes pods. When storing encryption keys in OCI Vault, you, the customer, are the only ones who can access these keys, and you are in control of the complete life cycle of these keys. This means you can decide when you want to rotate your keys on your own time frame. We've just covered how to secure the actual Kubernetes infrastructure. Now let's talk about how we can secure the containers that you're running within your Kubernetes cluster.
Yeah, the next level of security applies to the containerized application that you deploy. Your applications are the last vector of attack. You can ensure that bad actors are kept away from your container images. So of course you can deploy images from any registry, Docker Hub for example. But the registry in OCI is OCI Container Registry, or OCIR for short. It supports container images and artifacts such as Helm charts. You can easily add a vulnerability scanner to your images to ensure that your application's images are free of serious vulnerabilities. Further, you can ensure that the integrity of your application images is preserved when it's deployed by enforcing image signing. And by allowing only signed images to be deployed in your cluster, you protect your entire fleet of applications from malicious code that might be inserted in compromised images. And you have the confidence that what's deployed are the same trusted image that you previously signed. Next slide.
It is important to ensure that your pod or containers can only execute based on least privilege. This means only give them the permissions that they need to execute the task or job that's specific for that container. This is achieved through Kubernetes by setting your pod security context. The below list is the minimum recommended security context that we recommend setting for your pods. This includes ensuring that you are executing your pods as non-root users, read-only file systems, not allowing privilege escalation, requiring only the capabilities that are required for that capability, not allowing any access to that host file system, and specifying requests and limits. For an extra level of defense, customers can add an admission controller, such as Gatekeeper, to their cluster. This admission controller can be used to define a policy for the cluster and ensure only compliant workloads are scheduled. The CNCF recently released a white paper going into details on the importance of Kubernetes policy management and having a policy enforcement point. Next, we will go over a couple of security context examples and how you can achieve these. For the first example, we will look at making sure containers are executing as non-root users. This is important since root provides the largest amount of privilege, and if exploited, could allow nefarious users to gain unrestricted access to a host. The first step is to build your container in a manner that the process is executing as a non-root user. In the Docker file example to the left, we see the run command. This executes two Linux commands, the add group and add user. These commands will create your user and group named node with non-root UIDs of 1,000 and 3,000. Next, within this Docker file, we can set the user to be node. This tells the container that we are expecting this process to be executed as the node user. Next, we will want to actually configure Kubernetes manifest file for this deployment to ensure that the security context is set to match what we described in our Docker file. In this section, we can assert that the container should run as a non-root user and have the UID and GUID we described above. If for some reason a container does not actually fulfill these conditions, Kubernetes will not start that container. So this is that extra level of defense. Next, we'll want to look at an example of running pods with read-only root file systems. Containers are designed to be treated as ephemeral entities, so it makes sense that the root file system within this container is immutable and read-only. This helps to improve the overall security posture. Let's take an example where a container has been breached and a user is looking to install a malicious binary within the container to execute. If the root file system is read-only, this will not be possible. The first example on the left, we see we're setting the security context for this pod to have a read-only root file system. There are, however, cases where your container or your application within your container might need to write some temporary file. Typical use cases for this are going to be writing a state file, cache, etc. If the root file system has been set to read-only true, there is no way to write this. However, as a container, I can still mount a file system into this container. The example on the left, we see the var run directory has been mounted into my container and it is backed by an empty dir. An empty dir within Kubernetes is an ephemeral temporary type of storage that can be used to write these types of cache in a secure manner. Next, we'll want to talk about, once we've secured our container environment, runtime environment, our containers running within that cluster, how do we monitor for ongoing threats that might be occurring?
Monitoring the user and application activity on your Kubernetes cluster is important to detect any anomalous activity or security breaches. All Kubernetes events, audit events, are made available in OCI audits. This service offers a consolidated view of all user activities across your applications on OCI. You can quickly identify security incidents, such as whether your cluster is under attack by observing successful and unsuccessful logon attempts. You can easily correlate Kubernetes audit events to other audit events in your tenancy, in your OCI tenancy. For example, lifecycle updates to your clusters or any other resources. Next slide.
Next, let's talk about continuous security assessment. It is important to continuously monitor and detect your configuration within your tenancy adheres to security configuration best practices, and also monitor for deviations from this configuration and any possible threats within your tenancy. Oracle's CloudGuard can be used to examine your OCI resources for security weaknesses. Upon detection, CloudGuard can assist with the triaging and resolutions of these security weaknesses. This provides users with a unified, holistic view of their overall tenancy's security posture. In addition, customers can leverage security zones to actually prevent configuration that may lead to a security weakness. CloudGuard provides users with out-of-the-box security recipes that can be used to streamline the detection of security weaknesses. This helps customers keep up to date with the ever-changing security, compliance, and best practice requirements for your OCI tenancy. In summary, when looking at OCI and containerized applications, in order to ensure that they're safe from malicious activity, we like to look at the multiple layers of defense. In summary, the first level is that cluster level. We talked about network security, how to ensure proper authentication and authorization access, how to encrypt your possible sensitive data. Next, we looked at the container level. We talked about how to ensure a proper supply chain assurance for your containerized images, how to ensure your containers are running with the least amount of permissions that they need. And then finally, how to continuously monitor and detect threats within your tenancy using audit logs and CloudGuard. Thank you for taking the time and listening to our presentation, and we hope that this has helped to ensure a secure Kubernetes cluster and containerized workloads.
Thank you.